it's quite the problem you got there. Let me see if I can help you figure it out. Okay, so basically we have a trough. It's being filled with liquid that has a certain density. Looks like it's 835. And essentially the sides of this trough are an equilateral triangle with lengths 10. When I forgot to put in the particular measurements here. So here's kind of a picture of it. It turns out that this length is 10. I don't want to start typing. See if I can get rid of that. That's not going to get rid of it. There we go. This length here is 10, as is this. The entire length of this is 10, which means that this side is 5 meters and this side is 5 meters. And the height here is going to be 10 cosine 30, because as you know, this angle is 60, so I have that's 30, which would be 10 times the square root of 3 over 2, or 5 root 3. So this height right here is 5 root 3. Well, this is basically an application of the Riemann integral concept. But basically, what we want to do is we want to divide this entire cross section into little slivers or little pieces of area. Identify what that area is. Compute the water pressure at that area, which of course you know is pounds per meter squared, and then then the force for the sliver is going to be the pressure times the area, and that will give you the force. And if you add them all up, you'll get an approximation to the total force. And also if you take the limit as the areas go to infinity, or the delta y, or the thickness goes to 0, the delta y becomes ty or dy, and we magically have an integral. So the first two parts of this problem are to compute is to look at each sliver and compute the area of each sliver. And then we also want to compute the pressure at each sliver. We will call P sub I. Okay, so let's start off with the area. The area is going to be equal to the width right here times the height, which is delta y sub I. Of course, now the width is nothing more. Now, I was hoping to make it clear in the drawing, but basically this width is nothing more than twice this length right here. So we can call that 2 times x sub I times delta y sub I. Because we're looking at the ith sliver right here. All right. So what you'll notice here is that this triangle and this triangle are similar. If that's the case, then the sides, then the ratio of the sides form a proportion. Specifically, this side, the ratio of this side, x sub I to y sub I, is going to be equal to the ratio of this side, which is 5, to this side, which is 5 root 3. So we will have x sub I over y sub I. It's a lousy sub I, but whatever. It's going to be equal to 5 divided by 5 root 3. And that implies that x sub I is equal to y sub I divided by root 3. And then our area is going to be 2. Let me rewrite that 2. That 2 is pretty pathetic. 2 times y sub I times delta y sub I divided by root 3. Unfortunately, the whiteboard is connected to the Wyzant site, which means we're going through the internet to make all this happen, which slows things down just a tad. Okay, so that is our area. That was actually what we were looking for in terms of area. Now, the pressure at this depth is going to be equal to the density, which we'll call, which for lack of a better term, just go ahead and call it rho, times the gravitational force, which is g, times the depth of the ith sliver. This is the depth. Now you'll notice that I have this height y sub I called out, so the depth is nothing more than the height of the trough. Well, actually, let me rewrite this part over here. Rho g, and then the depth is nothing more than the height of the trough, which is 5 root 3 minus y sub I. Sorry, y sub I. So here's the depth. You go down 5 root 3, go back y sub I, and there's your depth. So that's what we got. So if that's the case, then the force on the ith the force applied at the ith layer or ith sliver would be, let's not do that, will be rho g 5 root 3 minus y sub I times 2 times y sub I times delta y sub I divided by the square root of 3. If I wanted to simplify that, or if I wanted to rearrange that, which I do, I would have f sub I is equal to, so I'll get all the constants over here, 2 rho g over the square root of 3 times the quantity 5 root 3 times, well, that's not a 3, that's a y. 3 times y sub I minus y sub I squared. And of course, all this is going to be multiplied by delta y sub I. Okay. Well, in that case, then the total force, or an approximate, or then the total force is going to be the sum. Oh, maybe back up. It's going to be the sum of all the forces, or of the force from all the slivers, as we make the slivers smaller and smaller to the point that they're infinitesimal. And if we do that, that basically means that the number of slivers are going to increase to infinity, which of course is then the limit as n goes to infinity. And this is just the arguments we use to turn this into an integration problem of the sum as I goes from 1 to n, 1 to n of 2 rho g over root 3, that's almost poetic, times 5 root 3, it's supposed to be root 3, there we go, y sub I minus y sub I squared delta y. And yes, using what we know about Riemann sums and their limits and everything, this turns into 2 rho g over root 3 times the integral from here all the way to here, which is 5 root 3, 0 to 5 root 3 of 5 root 3 y minus y squared dy. Okay, let me see if I can make myself some room here. I didn't want to do that. Does this thing go down? Please go down. Or maybe it just goes over. Okay, anyways, it turns out that evaluating this integral, you will have, and let me just do this up here since I'm actually running out of space. 2 rho g over root 3 times 5 root 3, and then and this integral, the integral of y, of course, is y squared over 2. We're going to evaluate that at 0 and 5 root 3. Minus, and I'm just going to rewrite this over here again, and you'll see why in just a second. 2 rho g over root 3, and now we will have y cubed over 3 evaluated at 0 and 5 root 3. Clearly, these things do not need to be evaluated at 0 because we'll get 0 on both terms. So for the first term, where am I going to do this? I know, I'll just make myself disappear. You don't need to look at me anyways, do you? All right, so the first term, and since I'm kind of going in a weird order, I'm going to change colors real quick. For the first term, we will have 2 rho g over root 3 times 5 root 3 divided by 2, and then y squared, and y squared evaluated at 5 root 3 will be 5 squared, which is 25, times root 3, which is simply 3. That'll be minus 2 rho g over root 3 times times y cubed over 3. Let me just bring the 3. Let me bring the 3 back here. So then we're going to have 5 times the square root of 3. That's supposed to be a 3 cubed. So 5 cubed is 125. And the square root of 3 cubed is really nothing more than 3 times the square root of 3. Well, now, isn't that convenient? Let's take a look at what we got going on the right-hand side before we move to the left-hand side. On the right-hand term, these cancel. I love when that happens. All right. On the left-hand side, this cancels that. The 2's cancel. And so on the left-hand side, or for the first term, specifically this term, we will have 5 times 25, which is 75, times 3, which is 375, rho g, minus 2 times 125 is just 250. So you go through, and that's it. And then the answer comes down to 375 rho g minus 250 rho g is just simply 125 rho g. So after all those numerical gymnastics, it just comes down to this. And then when you apply the numbers, you will have 125. And forgive me for excluding the units. That's actually bad form, but I'm going to do it anyways. Times 835, which is your density, times 9.8, which is your gravitational acceleration. And that will give you 1,022,000. Supposed to be a 2. 1 million. Let me just do that over again. 1,022,000 and 875 newtons. And that is how you do your problem. Remember, this is the problem where you basically compute your areas. Once you got your area, you just basically integrate on through. And of course, this is the standard rationalization you have for going from summations down to the integral as delta yi shrinks down to 0. Well, anyways, I hope this makes sense, and I hope you found it useful. And again, if you have any other questions or need some help, again, my name is Bob. You can find me on the tutoring platform, and I'd be happy to give you help you out as best as I possibly can. Thanks, and hope you have a good evening.